Hi everybody again. I'm Susana Reyes from Excimer, and I think the reason I'm here is because before moving into project management and management of fusion engineering, I started my career in nuclear safety. I did a bunch of studies for the nuclear analysis of the National Ignition Facility, the chamber, the worker doses, and then at ITER, when Carlos was there developing accident scenario simulations for the licensing documentation for the ITER project in France. So I don't love regulation as much as Patrick, but I'm quite familiar with the topic from both sides of the technology, from the laser fusion side and the magnetic fusion side. Okay, so for people that are now in commercial fusion development, having regulatory certainty is key to move fast. So in that sense, in the US, there has been quite a large amount of work that the fusion companies have been doing together with the Fusion Industry Association to try to provide options to the NRC, and the NRC has been looking at the different ways of regulating fusion, and in April of 2023, it was voted that after looking at the different possibilities, they were going to regulate fusion under 10 CFR Part 30, that is the particle accelerator framework for byproduct material. That doesn't mean that it's easier regulation, that is going to be less safe. I happen to have worked in particle accelerators. I took a little break from fusion and I went to manage particle accelerator construction at Stanford and at Lawrence Berkeley. And I know particle accelerators can be very different in terms of hazard. So what Part 30 provides is the flexibility to tailor the safety envelope of the facility and the safety requirements to the level of hazards. That is, I think, what many in fusion are looking for. So the proposed rule has been published recently in May, a week ago, and now there will be an opportunity for public comment, and the goal is to move towards finalizing, making the rulemaking final by end of 2026, which is extremely timely for the fusion companies in the US that want to deploy their break-even machines in the next few years. Okay, so technology roadmaps for fusion need to take safety consideration into the design from the early stages. So now, in my case at Excimer, we are developing lasers for fusion. This is some of the systems that we have already deployed, a long pulse kinetics platform here on the right for studying the krypton fluoride kinetics. We have some Excimer lasers on the top. In the bottom, there is a large tube for studying stimulated brilliant scattering for pulse compression. All of these systems, of course, we are focusing on laser safety. These systems don't have tritium. But as we learn to make laser systems that are bigger and bigger, we are incorporating safety into the culture, into the organizational culture. So here is the roadmap for Excimer. We are in the first stage here that is called Phoenix, the Phoenix facility in Denver. We are going to move forward to making like our first plant scale laser. And then the Vulcan facility is the first facility that is going to have tritium. It's our break-even facility that we're planning to use for demonstrating commercial break-even. And in this facility, the amount of tritium will be around 10 grams of tritium, right? So more or less like Spark. And then the 10-year vision, the next decade, is when we are planning to deploy a pilot plant that will be larger amounts of tritium, larger radioactivity, and so on. So looking a little bit different. So, key considerations when designing these systems. I'm not going to talk about lasers. Now I'm going to talk about fusion chambers. So, key considerations: to minimize the radioactive source term and to minimize the energy sources that can mobilize that radioactivity, right? So, minimization of chemical reactions that can release large amount of heat, or minimization of hydrogen production in accidents that can lead to explosions, because all of these energy sources can then mobilize the tritium and the radioactive source them. So this has to be considered from the conceptual design stage. It cannot be an afterthought once we are in the more advanced design phases. Low occupational doses through minimization of maintenance activities and optimization of shielding. and low operational releases, so control of the effluents to make sure that during routine operation we are limiting our releases of tritium through the stack and so on, and acceptable accident consequences. So this is something that needs to be assessed early on and discussed with the regulators so that we understand how a given fusion technology compares to a given particle accelerator or a fission reactor. And not all fusion technologies are created equal, so the safety bases will look quite different for a demo, for a Commonwealth ARC, and for a Excimer pilot plant. So that's something that we also need to consider. And final consideration, waste. From the early stages of the design, there has to be an assessment of material activation and waste volumes to minimize the waste streams and to minimize the level of activation of the waste for public acceptance and for ease of licensing, of course. Let's see. We've been talking a lot about partnerships and so on, so I just created this slide last night to show that in the case of Excimer, like many fusion developers, we are using private-public partnerships for very critical areas related to safety, including tritium systems and neutronics. So we have an excellent collaboration with the UNED University in Madrid for fusion neutronics. They have an amazing team that they are also doing neutronics for ITER and for DONES. Yeah. So we are leveraging that talent in the University of Madrid to support us with all the nuclear analysis at this stage. We are working with Susana Reyes in the lower left. We are developing a process for tritium extraction from molten salt that can also provide redox control, chemical control of the salt to avoid the formation of free fluorine. This is very, very important in molten salt systems to avoid the formation of free fluorine that can create corrosion. So we are at the early stages of demonstrating this technology with Savannah River, and we are partnering with other companies such as Commonwealth Fusion in the Liberty program. The Liberty program is a public program from the UK. The UK government has provided some funding for creating this facility that will be a test bed for bringing a breather module and testing it with 14 MeV neutrons and measuring the breathing and more than the breathing that we know we can breathe, what we need to demonstrate is that we know where the tritium goes and that we know to extract it. And we don't lose it to the structures, we don't lose it to the room, and so on. So very important activities where collaborations with the public sector are key. This is triggered by some comments from Klaus. He was talking about the total inventory in the plant. This is key. I think that this has to be a piece of the early stages of the design of any plant, any fusion plant, understanding where is, don't try to read it, I know it's very small, but understanding where is the tritium and how much is and in what chemical form, and is it interacting with other materials in the plant and so on. This is critical, and we are working on this with a code that is called Aspen Plus that is similar to what Teresa Dominguez mentioned yesterday. EcoSim Pro, I think, is the code that her company, Empresarios Agrupados, is developing. It's a very similar thing. So lots of opportunities for collaboration also in this area. And just to close this presentation, just copied here the questions that Francis sent me a few weeks ago when preparing for this panel. And the questions are, which regulatory approaches are proving effective and which risks are being prioritized? So I think that right now in the US, the companies that are moving forward with their scientific break-even facilities are finding the proposed Part 30 to be appropriate. Risk prioritized are, of course, the sources of energy, I guess, in magnetic fusion devices, controlling the magnetic energy and controlling the tritium inventories, of course. How to balance innovation and safety without replicating frameworks for fission. I think that in the case of 10 CFR Part 30, it's a performance-based kind of regulation. So the regulator sets the objectives, and it's up to the developer to demonstrate that they can meet those objectives. So it doesn't mean that one has to compromise between innovation and safety. I think that there can be a lot of innovation with the proper safety demonstration. Same as in particle accelerators, where all of the particle accelerators where I've worked in the DOE system, they are very first of a kind, very innovative, but there is a safety envelope that looks very different from particle accelerator to particle accelerator to let them operate while meeting the objectives for protection of the workers, the public, and the environment. And then finally, lessons that might inspire Europe to develop a more agile and proportionate regulatory frameworks. I think that there are many lessons learned from ITER. Carlos can tell you about this. Lessons learned from ITER licensing and things to avoid, to have requirements that are over-dimensioned and can drive your cost and schedule beyond the desirable. And some lessons could be learned from what UK and the US are doing in terms of adopting other type of regulations.